This episode is brought to you by Skillshare. To fuel our future in space, we will need massive industrial production up in space, but how will that develop? And will the creation of such industries to help colonize space also influence how and where that colonization occurs? We've recently been discussing the development of industry on the Moon and how that might serve as a base for expansion into the solar system and beyond. Today I thought we might look at how various regions of the solar system might develop industrially. So we'll be looking at how space around the Earth and Moon might develop, and what directions we might go in for the asteroid belt, Mercury, Mars, and Jupiter as well. Indeed, we'll move out not just the Kuiper belt and Oort cloud, but also take some time near the end to look at this notion at the galactic level. Industrialization of space is a peculiar thing, since so much space pioneering speculation and science fiction focuses on Mars and other off-world colonies, but in truth I'd rather expect worlds like Mars to be a fairly minor player in a developing solar economy, and I'd also expect the space right around Earth to be where the supermajority of industrial development and colonization occurs for many centuries to come. It's commonplace to imagine humanity numbering 1 trillion people spread over many worlds and many systems within the next few millennia, but I don't think we'd really be all that spread out in reality. If I had to guess what the landscape would be like for humanity when we first hit 1 trillion people, well, I'd not be surprised if we had colonies of millions of folks on other planets and moons and even in other solar systems. I'd also expect 99% of the human population to live either on Earth or in orbit around it. You could pack a lot more than that rather comfortably into space habitats orbiting our pale blue dots, and indeed you could do it on Earth itself if you wanted, but while orbiting habitats might not be as ideal a place to live as Earth, they will generally equal or match the comfort you'd find on any planet that wasn't a particularly rare clone of Earth. We don't know of any planets that qualify as true Earth analogs, and the nearest match is actually Venus, not Mars. However, while Venus is definitely a candidate for terraforming, as we looked at in Winter on Venus, that's not a fast exercise. Many centuries will be required to get people onto Venus, if not more, and far longer to make it anywhere close to Earth-like if you want to do it that way. So odds are folks living in space will be living in a rotating habitat anyway, and one nice and close to Earth is likely to be the preferred locale. It's also where most of the firsts for space development are likely to occur, so it makes sense to start there first. Whether it's a space farm, spaceport, shipyard, or a space hotel, some place in low or medium orbit of Earth would seem where we'd see the first one built, and probably almost all of the early ones. Some might appear on or around the Moon too, but the Moon orbits Earth so it arguably qualifies, particularly as the travel time and communication lag to the Moon is tiny compared to even that of the nearest planets and asteroids. Of course, it's even shorter to low orbit, which is closer to us than most of our neighboring states or nations, just a few hundred kilometers up. It's an area larger than Earth's surface, and it's also three-dimensional, so you can pack plenty of stuff in there, and far more into medium orbit. Indeed, Earth's Hill sphere, the volume of space in which an object would orbit Earth rather than orbit the Sun, is 1.5 million kilometers in radius, over 200 times wider than Earth, and containing 11 million times the volume and 50,000 times the surface area for the purpose of either collecting solar energy or radiating away heat. If we treated that surface area as effective living room, then if the cloud had a population density parallel to my own home state of Ohio, it would house a couple quadrillion people. Ohio is hardly densely populated either, so such a setup could easily be mostly composed of space farms and nature preserves, and it could be many times that number without feeling packed or even vaguely urban. As to signal lag, even those most distant parts of it would only be 5 light seconds away, permitting a message to be heard and its reply received just 10 seconds after you sent it. That's an irritating pause for live communication, but mostly just irritating, not troublesome or impractical, whereas all but the closest planets would need hours to get a message back and forth. That's one of the reasons why this region would be the one to get developed. It has proximity to where we are now, and where most things will be for at least several centuries, not because it has a lot of resources, though indeed it does. Earth is the most massive terrestrial planet, being around the combined mass of every other rocky planet and moon and asteroid combined, and Earth's moon is one of the most massive moons in the system, and indeed outmasses the entire asteroid belt by a factor of about 30. There's a reason a lot of businesses and factories get set up in big cities, not just because that's where the workforce is, but because that's where most of the customers are. Earth's orbital space is likely to be the same, and we'd expect that to repeat around other planets or places where lots of people or activity are going on. The eventual fate of most planets is likely not to be turned green and visible as blue and green dots through telescopes, but instead to appear as far bigger blobs of orbiting infrastructure gravitationally anchored to that planet, be it terraformed or not. They would enclose those worlds like a thin hazy fog or cloud, almost like a second atmosphere, though you can control your orbits of those habitats to avoid blocking sunlight to the planet below. As such places grow, they need more infrastructure and industry, and those will generate their own growth in other sectors. After all, if you build a factory and employ a bunch of people, those folks all have funds and a desire for restaurants, shops, and schools nearby, whose own employees need the same, resulting in more, and so on. However, this might not result in a big spherical blob, but something more like a bracelet or maybe a ring with a gemstone. We'll come back and explain that in a bit. Now, I should note that as we saw in our Outward Bound series, colonizing a place does not necessarily mean a lot of people live there. You'd expect any major effort to make use of a ball of rock to result in migration, but a place has to have an appeal to live there, and most folks don't opt to live in mine shafts, just work there. And even then, the march of technological progress on automation means fewer need to work down in that mine, or even necessarily live anywhere nearby. As various industrial belts and regions in the solar system develop, we should not assume that colonization implies a proportional amount of immigration. Some massive factory the size of a mountain, with an industrial output that exceeds the entire current global economy, might have a crew of a few hundred, and only a small habitation drum for a cozy little village. Or it might be totally unmanned, for a given value of unmanned. It might be manned but not by classic humans. They might be cyborgs, digital consciousnesses, artificial intelligences, or subhuman intelligence robots, or even genetically engineered creatures, such as we contemplate in the episodes Void Ecologies and Space Whales. It's entirely conceivable some system might reach full Kardashev 2 development levels, where one has enclosed an entire star in what's called a Dyson swarm, and still have virtually everyone living near the homeworld. A Dyson swarm might be expected to have 1 billion times as many people as we have now living in it. And yet if most food and industrial work is imported into the region most folks live in, it might only need to be about the size of Earth's hemisphere to allow it to be big enough to get rid of all the heat generated by its inhabitants and their basic services. Not many folks might need to live outside this volume. After all, modern farms require very few workers compared to how many folks they feed, and a futuristic space farm might be merely a small village of overseers monitoring the production of those space farms close enough to be remotely supervised and overseen, potentially having a few hundred folks handle food production for 1 billion people back home near Earth. But let's get a bit nearer modern Earth, at least in time. Our first big industrial effort away from Earth and its satellites, natural or artificial, is likely to be in the asteroid belt. Not because it has a ton of resources, there are a couple dozen planets and moons in our system who have as much or more than the entire belt, but because they are so easy to get access to. It takes very little fuel to move around the belt or move material off a given asteroid, and you needn't dig much to get access to any of it. It just doesn't take much fuel to access those resources, and that's what mostly matters. When we're talking about raw materials, time doesn't matter much in the equation because they don't spoil. So long as the market is reasonably stable, you could sell metals you just mined off an asteroid for a good price today, even if they wouldn't arrive at the places that wanted them for a decade while they traveled along at minimum fuel trajectories there. Of course, time does matter, and there's the threat of market fluctuations or losing the cargo, or getting stolen by space pirates. But like many commodities that have a long shelf life, their price can fluctuate simply by a report a new supply of them has been found, and they can effectively be traded and sold before the first mining equipment even arrives there. They are fungible, meaning you don't care about the individual bit, one chunk of gold or iron is the same as any other, and effectively nearly as good as cash. As we saw in colonizing series in the asteroid belt, assuming the process is nearly entirely automated, you'd expect to see this region develop probably before any other bit of the solar system, excluding Earth's volume, with colonists following along to provide food and other services. Long-running mines might develop into settlements, and abandoned asteroids full of holes might get resold to serve as habitats for humanity, as we crammed in rotating habitats and space farms and other facilities. But raw resources are never as valuable as the end products they are turned into, and such settlements would want manufactured goods too. Plus, who wants to ship wealth home to Earth only to have to spend a lot of it buying back manufactured goods? We'd probably begin seeing industries develop there fairly soon after folks began arriving for mining. An interesting parallel might be the gold rush to California in 1849, and while that was hardly the only reason folks migrated to California, it's a reminder that a century of development can have some surprising twists and turns on the original motivations for going there. Silicon Valley and Hollywood have no obvious correlation to gold, and yet California is far better known for both of those economic powerhouses than its gold production nowadays. So too, much of the effort to originally colonize the United States was driven by wanting to grow tobacco and some other products, and while that surely shaped the nation that came, it's not really obvious how those early plantations would lead to becoming a superpower that has been a driving force for our efforts to get into space. For this same reason, while I said earlier I'd expect most folks to live on or around Earth for many centuries to come, a place like the asteroid belt could easily become a major population center, or ring anyway. Our first industrial belt in space, in a literal geometric sense at least. Where else? Well, of course there's the Kuiper Belt, the much bigger brother to the asteroid belt out beyond Neptune, but it's far away so we'll come back to it. We also have Venus and Mars, and they could easily develop their own big bubble of industrial might. We should not assume gravity wells and the fuel cost to climb out of them is really that much of an impediment. After all, we need to get better at that to realistically get space development going in the first place, as Earth's gravity well is far larger than any other place in the solar system besides the gas giants in the Sun, which we presumably aren't planning to land on, though I imagine channel regulars already can guess that we are going to discuss doing exactly that later in the episode. Advanced launch vehicles and structures may help seriously reduce this cost, and you can see those in our Upward Bound series, and structures like the orbital ring can potentially make this rather cheap, even if they have a large initial cost to construct, much like railroads or canals. Similarly, while we lack any material we can build a space elevator out of at the moment, that's only true for Earth, and many of our larger moons and even planets could have space elevators built on them using only modern materials. We would need to gain access to them eventually, as they are where virtually all the mass and resources are, but we tend to assume this need would be long down the road, and we'd start with the low-hanging fruit in the low-gravity asteroids and smaller moons. However, with sufficient energy abundance or infrastructure, the actual cost of moving material off-worlds and in between might be low enough that gravity wells might not be a big concern, or that minimum fuel trajectories for raw materials might not be worth the cost. After all, we regularly fly cargo around rather economically these days instead of shipping it by slower, more energy-efficient methods. The cost isn't that high compared to the final product in many cases, and what's more, fuel is not the only cost to shipping. Haste doesn't always make waste, and if you're paying salaries to a crew, or for maintenance on a ship or insurance premiums against space piracy, it might be cheaper overall to move that stuff fast, or source it from deep down a gravity well. That's particularly true if your gravity well is in the middle of your marketplace. So same as Earth might develop a massive swarm of habitats around it, eclipsing its own living area and population, Mars or Venus might develop their own swarms around them, causing a growth boom around them that feeds on itself and that world below. Of course, in the outer planets, this growth might begin entirely off that planet. For places like Jupiter and Saturn, where there's no land anyway and where there are many moons, big and small, you might see all those moons settled fairly quickly. In many ways, these gas giants and their moons are like little solar systems all their own, and not that little at that. Being rather far away from the sun, solar power is an option through using cheap thin mirrors to concentrate light for collectors, but I suspect you'd only see major settlement of such worlds in a fusion-based economy. Were that the case, these moons would have enough hydrogen or deuterium to run an empire dwarfing our own civilization in scale, and fueling it for eons to come from those massive worlds below. Those moons themselves are hardly low on resources either. The largest of Jupiter's moons, Ganymede, is roughly twice the mass of our own moon. While often less dense than our own from having more ices, they are still abundant in metals. Those ices also likely contain other substances than just water, such as ammonia, a great source of nitrogen which would be necessary for building habitats. These gas giants also have rings, albeit most far less grand than Saturn's, and they might pick up far more grand rings as we settle around them and fill their orbits with artificial habitats. Again, these gas giants have the possibility to become not so many solar systems all on their own, and their close proximity of their moons to each other in distance and fuel needs means that from the very outset, you'd be able to have a robust trade between those worlds. Even very primitive spaceships, far inferior to those we first used to reach orbit, could ply the space lanes between a gas giant's moons, and you presumably have far more sophisticated ones to have settled the region in the first place. Indeed, if we ever have an interplanetary nation, one that rules over the entirety of multiple worlds, it's likely the first example would be around these gas giants and their collections of dozens of moons. Though in fact they arguably have far more than that, particularly Jupiter, which we'll discuss in a moment. Far more grand options are available though. As we discussed in colonizing Jupiter, it should be possible to strip away all the gas around the planet to expose the rocky inner core, and transport that gas to storage facilities to be used as needed. Now in Jupiter's case, you'd not likely want to terraform that core, as it's theorized to be several times Earth's mass, indeed might be a giant diamond, but certainly the material there is of great worth, likely containing more metals and heavier elements than the rest of the solar system combined, minus the Sun of course. For those other gas giants, their cores are less massive and might be something you consider terraforming, though they are far from the Sun. In theory, all that gas makes excellent fuel and propellant to move a planet inward, using what we call a fusion candle, a massive fusion thruster. But in practice, if you have such a capability, large-scale artificial fusion, then you could easily make the equivalent of an artificial star to light that system, which is certainly preferable to the occasional suggestion of turning those gas giants into mini-suns themselves. See the episode Making Stars for details on the options there. Of course, you could also simply run fusion power plants to produce electricity to light habitats instead, or to run large mills to create meals and dishes to focus sunlight on those moons or gas giant cores. The amount of material and energy needed to make enough of them to light that region to Earth levels is immense, but tiny compared to constructing vast numbers of habitats or disassembling smaller moons for the resources to make them. Let's return to my remark about Jupiter having more moons than those directly circling it. Every body that orbits a significantly larger body, be it a planet around a star or a moon around a planet, creates a quintet of Lagrange points, places where an object would move along with the smaller orbiting body. Normally objects orbit faster the closer they are to the primary that they orbit, and slower the further they are. However, that's not always the case. There's one point on each side of the orbiting body from when it orbits that will stick along with that orbiting body even though it's closer or further from the main body itself, and thus should go faster or slower. The L1 point, which is between the bodies, and orbits a bit slower than it should at that distance, from the satellite pulling it away from the primary. The L2 point, which is behind the satellite, and things there orbit a bit faster than they should, with the satellite adding its gravity to the force the primary exerts on that L2 point. Such points are very handy for placing things like solar mirrors or lenses. There's also the L3 point, which is on the exact opposite side of the main body from the satellite. However, we have two other semi-stable points, the L4 or L5 Lagrange points, also known as the Trojan points, which are 60 degrees ahead and behind of the orbiting body, but on the same orbital path. You might wonder why these are stable, but essentially, while they are pulled toward that orbiting body, at the 60-degree mark, forming an equilateral triangle with a satellite in the primary, the ratio of forces remains the same and they are stable, or reasonably stable. Objects on the same orbital path, but not at the L3, L4, or L5 points, will end up falling out of that orbit. Now we call the L4 and L5 Trojan points because our first examples were a cluster of asteroids and debris in front and behind of Jupiter on its orbit of the Sun. Other planets have them too, but Jupiter, which is essentially the solar system's vacuum cleaner, has far more. Keeping with the mythology we borrow the names of Jupiter's moons from, we named those various objects at the L4 and L5 after characters from the Trojan War, the L4 being known as the Greek camp and the L5 the Trojan camp, though as our telescopes improved we found far more of these objects than there are characters in Homer's tales to name them for. Needless to say, these are excellent candidates for colonization too, as they are spread out rather widely and have a total mass about a fifth of the asteroid belt. It takes very little energy to move between them or back and forth to Jupiter's main moons too, so this could easily become a second literal industrial belt, albeit a bridge rather than a full circle, or donut anyway. The asteroid belt is a rather large volume, as is the space occupied by the Trojans, and indeed we could do similar setups around the other gas giants, not that it's limited to the gas giants. However, this raises another interesting point. When we say stable or semi-stable for large orbits, we are really only talking about natural objects performing mini-orbits over very long timescales. If I place an object 6.7 million kilometers from Earth, in front or behind it on its orbital path, a bit over 4 times as far away as Earth's hemisphere boundary, gravity has hardly shut off. But 6.7 million kilometers is 1,000 times further from the Earth's center than the surface we walk on, and by the inverse square falloff of gravity, an object 1,000 times further away experiences 1,000 squared or 1,000,000 times less gravity. We fall toward the Earth on its surface at 9.8 meters per second squared. An object at that distance would want to fall at 9.8 micrometers per second squared. Now over time it is going to pick up a lot of speed. Indeed, as tiny as 9.8 micrometers is, thinner than most hairs, it is only going to take about a day to have accelerated to walking speed, and within a year to be moving at the speed of sound on Earth. So on astronomical timelines it's not stable at all. However, it's very easy to provide enough thrust to keep it there, and indeed even a fairly small solar sail could be able to give it enough radiant pressure to stay where you want it to be. We call this a lagite, a body which maintains an orbital period lower than it ought to for its distance from the Sun because of using light pressure to alter the net force the object experiences. In this way, a space station with a large solar sail, for power collection for instance, could be on the same orbital path as a planet and remain stable without being at a Lagrange point. Indeed, it could also be outside that orbital path, being a bit closer or further from a sun, or above or below that orbital path too. Now normally you can only have a ring orbiting a body if it's fairly evenly spread, such as a planetary ring or asteroid belt or Kepler rosette, but the Lagite option allows you to do this even when you have a large single satellite that would dominate that orbit and perturb things. This means that not only could a planet have a large swarm of orbiting objects inside its hemisphere, but it could create a large ring all the way around the star of artificial stations. Indeed, they could be literally lashed together with a cable that provided a bit of additional stabilization and a cable car path all the way around a star. Such a physical connection can also be used for mass transport of goods, and if you're timing things right, you can use this movement of cargo to stabilize the ring. Indeed, you could also place very large storage depots of raw material or fusion fuel, hydrogen imported from Jupiter for instance, at those L3, 4, and 5 locations, along with the other two 60-degree increments to effectively create a Kepler rosette. Though since this would need to be Earth mass, you might as well make shell wards, and the mass involved would make this a mega engineering project of planet-building scale. The ring itself though could be used for mass transport of food and goods into the cloud of habitats around Earth, potentially turning this whole ring into something like a metropolis Earth, suburban cloud around Earth, and rural farming in the ring itself. It's almost unimaginable how many folks could live in such a thing, but we're talking many quadrillions and most could be on Earth or its habitat cloud. I occasionally call this the Terran Ring as I envision one possible path for our expansion being a planet swarm around Earth forming a gemstone with the band as a big ring around the Sun. If you wanted to get really elaborate, you could potentially create a super long thin rotating habitat along this entire path, what we call a topopolis, though such objects might wrap around a star several times, not just once. This would mean you could actually walk or sail or fly all the way around the Sun. Another version of this might use 2 of them with cylinder habitat rungs in between, looking like a very long ladder wrapped back around itself around the Sun, what we call a rung world, not to be confused with a ring world. These may be built around a planet too, of course, not just a star, and handily may be built without any super strong materials as a classic Niven ring world requires. I'm not sure I'd call the Terran Ring, or any other variation of this concept, an industrial belt in space, but I imagine it would certainly have a ton of industries on it or otherwise servicing it, and a Terran Ring might become another inner belt closer than the asteroid belt and of course artificial. Now you might see this reproduced around every planet, or others cocked at an angle to the ecliptic. This is one path to forming a Dyson swarm, and we discussed that more in our Dyson Sphere episode. And of course we might do something similar out in the Kuiper belt, which is more massive than the asteroid belt but far more thinly scattered. However, the Terran Ring, or one around Venus, might come much later than another ring or rings closer to the Sun. As we discussed in our episodes Colonizing the Sun and in Star Lifting, our Sun contains about 500 times the mass of the rest of the solar system, with half of that being in Jupiter. It similarly contains about that ratio of metals and heavier elements. There's already more than enough metals in the planet Mercury to construct a Dyson swarm focused on power harvesting, but you need far more heavy elements to produce a Dyson focused on habitation and industry. It's quite probable Mercury would be slowly harvested to create a ring or sphere around the Sun focused on power and industry, and it's possible that its main production would be the equipment needed for a massive starlifting project to begin harvesting those metals in the Sun. It's essentially impossible to express the industrial might such a Mercury ring supplied with power and energy from the Sun would have, even with modern technology for the output, but it's more than sufficient to power the construction of a Dyson and huge colonial armadas to venture out to the galaxy. Now, out in the Kuiper Belt and Oort cloud, you might see additional industrial sectors, particularly in an artificial micro-black hole-powered economy, but there's not much matter out there, and even less considering what an immense volume it is distributed across. And this takes us to our last potential industrial belt, the local bubble. A star is an immense thing, and even without its metals, our solar system contains more than sufficient quantities to build quite a massive civilization. But there are scenarios for going far larger, and also, if you want to colonize a galaxy, it can use up some major resources, especially if you'd like to send some of the giant colonial armadas we contemplated in the Generation Ship series. There are a lot of stars around us though, and with their own planets, what we often call the local bubble, and while these logically seem our first colonial targets, we may end up engaging in massive resource harvesting of them instead, shipping untold trillions of tons of raw material home while converting more into endless armadas and megastructures to be used in pioneering the galaxy, such as an interstellar laser highway system. The notion of shipping raw materials between stars can seem absurd at first, but for these kind of projects a few millennia is no time at all, so shipping material at low speed, low energy trajectories could actually be economical to a resource-thirsty system, as humanity's home solar system might be. We have discussed scenarios for constructs far larger than even Dyson swarms on this show before, and it's conceivable a Kardashev 2 civilization might decide to keep growing directly, rather than just seeding new solar systems, by mass harvesting of extra solar resources. Potentially thousands or even millions of solar masses are contained in one mega Dyson or Borch planet. Speaking of millions of solar masses, there is one last place of note. The center of most galaxies contains an enormous supermassive black hole, and as we looked at in our black hole series, such things represent the ultimate in efficient energy production, and could become the focus point of civilizations whose scale and industrial might can only be described as astronomical. And one might end up harvesting an entire galaxy, or even more than one, to create a massive but compact civilization that could minimize the problems of light lag normally facing a galactic civilization. Although amusingly such an effort might instead focus around Earth. It's popular to suggest we might move our galactic capital to the center of the galaxy, but when we're talking about moving millions of stars worth of material, you might end up just moving the center of the galaxy to Earth instead, or Earth to there. Such projects would require millions of years, and industrial and engineering efforts almost beyond imagining, but then again, we can imagine a lot, and it's exactly what such massive industrial belts as we have discussed today are ideal for. We were talking about industry and productivity today, and I often get asked how the heck I managed to write and produce a half-hour episode each week, along with getting bonus episodes done and doing everything else on my plate, like administering a primary election here in Ohio next week, or getting married next month. Same as with various creative skills like writing or graphic design, you really have to learn your own best approach, especially when your work is creativity focused, and just constantly be trying to figure out where you're getting stuck, wasting time, or need to improve, and also constantly looking at how other folks manage their workload for ideas you can borrow or adapt. If you're looking for some suggestions and ideas for either evaluating your productivity or improving it, I'd recommend Thomas Frank's course, Real Productivity: How to Build Habits That Last, over on Skillshare. He offers a ton of great suggestions that are pretty universal, and you can find plenty more productivity suggestions or courses on creative work like writing and graphic design among Skillshare's catalog of thousands of classes for creative and curious folks looking to improve their skills or learn new ones. A premium membership is less than $10 a month and gives you access to that course and all the rest, and you can try it out for free. To sign up, visit the link in the description, And as a special offer, the first 500 people to use this link will get 2 free months of Skillshare Premium membership. Act now for this special offer and start learning today. So last week we were looking at the Fermi Paradox, and next week we'll return to that to contemplate scenarios where alien civilizations are rising left and right and sending out signals for all to hear, but we are not hearing them and maybe nobody else is either, in The Fermi Paradox: Whispers in the Night. We also talked today about colonizing moons, asteroids, and lower gravity planets. And 2 weeks from now we'll ask what life on low-gravity planets would be like, be it naturally evolved there, transplanted and adapted with time, or even genetically engineered. We'll also ask how likely such worlds are to be able to have favorable conditions for life emerging, like atmospheres and oceans. For alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, hit the like button and share it with others. And if you'd like to support future episodes, visit our website, isaacarthur.net, to donate to the channel or check out some of the awesome SFIA merchandise. Until next time, thanks for watching and have a great week.